Today we are going to keep diving into HVAC. The entire rest of the course is on HVAC systems. I hope everyone was able to watch Thursday's lecture. I didn't check the number of views. There are 17 of you in this class, so I hope there's 17 views. The basics. Most HVAC systems that heat or cool a building or do both, they do that with conditioning of air, which, remember that term, HVAC, heating, ventilation, and air conditioning. The fundamentals of this are fairly straightforward. If my space is hot, well, let's blow cold air into a room. Let's turn on the air conditioner. Or if the space is cold, we turn on the gas heat or the electric heater and we blow hot air into a room. This is a very simple concept, but it is important to remember because HVAC systems, the large majority of them anyway, operate on these kind of principles. The means of how you heat or cool that air can change, and the method and how you deliver the hot or cold air, that can change, but that fundamental principle and what you get at the end result is going to be the same. In commercial applications, we talked about ventilation on day one in this class a bit. In commercial applications, meaning any non-residential, you typically have to run these systems all of the time to provide that ventilation air during those occupied periods. So even when that space, the thermostat on the wall says, hey, I'm perfectly happy right here. I don't need heating. I don't need any cooling. We still have to run that system to provide ventilation air. And that's a code requirement. A generic term for any system that has a fan to move the air and a heating or cooling or both component is called an air handler or an air handling unit, often abbreviated AHU. And the last thing, the airflow rate is typically expressed in cubic feet per minute, or CFM. Good old CBEX. Again, if we were to look at the combined heating, cooling, ventilation fans, what's the percent of the total energy use? In education, 57%. Office, right up there. Healthcare, same ballpark. Retail, HVAC is a little less. Lodging is quite a bit less, probably because more of their energy is going to domestic hot water. Similar with food service, most of your energy is probably going to your cooking appliances. But the point here is this is a big chunk of that energy use pie. And that's the reason why HVAC is the backbone of energy auditing on any commercial building. And that's why there's going to be so much focus on these kinds of systems from here on out. To put it visually, there are our CBEX charts. You can see those three components make up a really big chunk of the pie. Let's look at a typical air handling unit. There are a whole bunch of parts and pieces on this to identify and talk about, so bear with me. This box on the bottom represents our room, aka our space, aka our zone. You have your cabinet enclosure for your air handling unit. So this is the outside cabinet that's going to contain all of this internal stuff. This funny looking thing is our supply fan, and there is a specific reason why it has this shape, which we'll look more at fans in a few lectures, a little more in depth. you're going to be blowing in your hot or your cold air from your unit, and whether it's blowing hot air or cold air depending on what the space needs, and that's all based on this thermostat. So the thermostat is telling you how warm it is in the space and then telling this unit what to do. So we blow in this hot or cold air into the space, it mixes as it travels through the space, and eventually it becomes neutral temperature air. It's not hot or cold anymore as it's mixed into the space. And there we're going to suck that air back into our air handling unit. From there, we have some air that we need to exhaust to the outside. So that's usually called our relief air. We also have our outside air, because again, we have to bring in that ventilation air. The outside air and the relief air have to be in balance, because if you're bringing in fresh outside air, you also have to get rid of air in the same amount, or else you're going to end up pressurizing the space. And then we get to the cooling coil. So that's the device that is going to cool down our airstream to a lower temperature. The most common ways to do this are with direct expansion, or DX. That would be any refrigeration-based system. You could have chilled water, which we'll talk more about chilled water in its own module, or you could have evaporative cooling, which basically means they inject water into the airstream, which raises the humidity of the air, but it also has a cooling effect, and it drops the temperature of the air when we add water. And then you have your heating coil, which could be a gas-fired, either natural gas or propane. Those are going to be the most common. Electric resistance, hot water, or you could have a steam heating coil. So those are all methods we can use to add heat to our airstream. So what's this look like in heating mode? So let's say we're trying to maintain the space at about 70 degrees. And let's say the thermostat is detecting a drop in temperature, and so it's going to send a signal to the unit to provide heating. If we're maintaining it at 70, that means our neutral temperature that's getting pulled out of the space will be right around 70 degrees, which if you keep following that path, and then you're going to be exhausting some of that 70-degree air. And then we need to bring in outside air, which could be very cold. This would be a worst case day in Spokane, would be a 0-degree day. If you're mixing 70-degree air with 0-degree air, you're going to end up somewhere in the middle. So for this example, let's say it's 50 degrees. And the resultant temperature will be based on what the mix is. If you're bringing in more outside air, it'll be closer to 0, and vice versa. So this is our mixed air, or our entering air condition, which is a combination of outside air and recirculated air that we've pulled from the space. Now this unit, I said, is in heating mode. So we're going to turn that heating coil on with whatever heat source that happens to have, whether it's gas heat or hot water or steam, whatever. Our 50-degree air hits that heating coil, and then it leaves at a warmer temperature, say 95 degrees. And then that's what ultimately gets delivered to the space, mixes in, becomes neutral, and then you just have a cycle. So this unit is just running all the time. It's always supplying air in, pulling air out. It might change how much heat it's putting into the airstream depending on, well, maybe it's 0 degrees first thing in the morning, but maybe a couple hours later it's 15 degrees, and maybe we can cut back on our heating. And that's the basics of a heating system. On the cooling side, it's very similar. So normally we keep our rooms warmer in the summer. So say 75 degrees instead of 70, which means we're going to pull 75-degree air out of the room. We got to relieve that air, same temperature. And now we got a screaming hot day in Spokane, 100 degrees Fahrenheit. But the same principles apply. We're going to mix this really hot air with our moderate temperature air. And our mixed air will be somewhere in the middle. So let's say that's coming in at 82 degrees for our mixed air or entering air condition. And now the thermostat says, hey, we're starting to get a little warm in here. We need to turn that cooling on. We turn the cooling coil on, and now we're going to cool down that 82-degree air to 55 and then deliver that into the room. And again, it's just a big cycle. You're delivering cold air, mixes with the room, becomes neutral, gets pulled back, bring in more outside air, constant cycle. An important part of HVAC is this idea of sensible versus latent heat transfer. I'm not sure how much of this would have been covered in your thermodynamics or heat transfer courses. If it was covered, it may not have been covered in direct relation to HVAC specifically. So let's quickly cover it. Sensible heat refers to any transfer of heat energy that has a direct correlation to raising or lowering the temperature. So every BTU change in an airstream, whether it's heating or cooling, only affects the temperature of that airstream. So in other words, sensible heat transfer is all about that temperature change and nothing else, with no change in state, which you might be scratching your head because that might seem like a duh kind of statement. But in contrast to that is the latent heat transfer, which refers to any transfer of energy that's used to condense water in an airstream. Meaning every BTU change in that airstream is going to condense water, but not affect the temperature. So in other words, latent energy is all about change of state. You're taking water vapor and turning it to a liquid with no temperature change at all. So that's a lot of words. Let's look at it from a visual perspective. So if we have a heating coil, this is a cross section of a piece of duct or within an air handling unit. Any airside heating process is going to be entirely sensible heating, at least almost always. In this class, assume that to be true. So that means that all energy that's going in into the airstream will raise the airstream temperature, and there will be no change in the water content of the air. So if we got cold air coming in at 55 degrees, and let's say that's holding 0.005 pounds of water per pound of air, and then that's going to leave at a warmer temperature. Hang on 1 second. I need to intervene with my kids. Hang tight. Sorry about that. Perils of working from home. Okay, so we got our air coming in, cold temperature with this water content. hits a heating coil that's nice and hot, and then it leaves with the same water content that it entered in. So our temperature went up, but our water content, pounds of water per pound of air, stayed the same. You're probably groaning right now because you're probably getting some bad flashbacks from looking at this psychrometric chart. But this does help illustrate a sensible heating process. So on this chart, these horizontal lines, these are the humidity ratio lines, which is pounds of water per pound of air. If you're looking at, depending on the chart you're looking at, it could be in grains instead of pounds, but these run horizontal on this chart. So a sensible heating process, if we start over here and we move straight horizontal, there's no change in the humidity ratio because we're running parallel with those lines. But we are increasing the temperature substantially. So recall these numbers on the bottom. These are our dry bulb temperature readings. So this would be taking it from about 67 degrees Fahrenheit up to, say, 99, but no change in the water content. So the air starts cold, leaves hotter, but we have no change in our water content. So heating processes are easy. Cooling gets a little more complicated because cooling processes are typically a combination of sensible and latent cooling. When we cool down that airstream, some of that cooling energy will condense the water, and some of it will lower the airstream temperature. So the energy that's used to condense the water, that's the latent component. And then the energy that lowers the temperature is our sensible component. Any airside cooling process, just by the nature of how they work, they are naturally a dehumidifying process of that airstream. They are dehumidifying the air that's running through them. The reason being, the air that's coming in, that air is hitting a very cold coil in that airstream. And that coil is typically below the air's dew point temperature. And so the airstream actually sweats water out. So if you think of a cold glass of ice water sitting on your table, if you let it sit there, the outside of the glass will sweat because the glass is below the dew point of the surrounding air. Similar concept here. Our airstream is hitting an extremely cold coil, and so the water vapor in that air is going to condense out. So if we have really hot air coming in, say 85 degrees, that has a humidity ratio of 0.014 pound of water per pound of air. It hits this cooling coil, and this cooling coil actually sweats water out of it because that cooling coil temperature is typically much colder than the dew point of the air hitting it. That water sweats off the coil. We have to collect it in some sort of drain pan. We don't want it just going wherever. And then from there, we have to take it to a floor drain somewhere in the building. We have to get rid of that water, which can actually be a pretty big deal from a design perspective on figuring out how to get rid of that condensate, is what they call it, the cooling condensate. So our warm, humid air hits cooling coil, leaves at a colder temperature, and it also leaves at a lower water content. So as this air moved through this coil, it lost about a third of its water content. So the air leaves colder, and it leaves with less water than it had when it started this process. Psychrometrically, again, we have our humidity ratio lines running horizontal, and I said that usually cooling processes are a combination, but not always. You could have an entirely sensible only cooling process where you're starting at a warm temperature, you're running horizontal on the chart, which means no change in water content. You end up colder than you were when you started, but you haven't lost any water. That is possible. What typically happens though is it looks more like this. So you still have the reduction in dry bulb temperature because you're running from right to left. So that's your sensible component. And then the vertical component is you losing water in that process because you're moving down the humidity ratio line. So the air starts warm and then it's going to leave colder and usually with less water content. And I drew this line at an angle. That's not exactly what happens. That is the beginning point and the start point for a typical process, but the actual path would be it actually runs horizontal. So it starts out as a sensible only cooling process. And then as you approach the saturation line, that's when you start to see a dip. So it starts flat and then it drops towards the end. All right. So conceptually, that's what sensible and latent heat transfer is. But how do we apply some math to that? If we know an airflow, if we know our unit is moving 1,000 CFM of air, how do we calculate the energy required to raise or lower the temperature of that air, depending on if we're heating or cooling? So we want our Q sub S, meaning sensible, in units of BTU per hour. We want that as a function of CFM, which is our airflow, and our change in air temperature. I won't walk you through the entire derivation, but just know that it's a function of the specific heat of air, 0.2403 BTU per pound of air per degree Fahrenheit temperature change. It's also based on the density of air. And you can see we have a 60-minute per hour conversion factor. We have our delta T. We have our cubic feet per minute. You work that out, you end up with units of BTU per hour of sensible heat transfer. And that equation is 1.08 times CFM times delta T. So our sensible heat transfer is entirely based on how much air are we moving and what is the temperature change of that air. It's not based on the water content whatsoever. And if you think back to the last lecture, the pre-recorded one, when we were talking about infiltration, this is the equation I just gave you at the time and said, trust me, this is it. But this is where it comes from. On the latent side, so if we know an airflow, how do we calculate the energy required to condense water out of that air? So we want Q latent in BTU per hour as a function of CFM and delta W, which is the change in the humidity ratio, pound of water per pound of air of that process. Run through similar steps, except this time we are using the latent heat of water for change of state. So that's to get water from a vapor to a liquid or vice versa, about 1,050 BTUs per pound of water. And we still have that density of air factor. If you work out the units, you end up with BTU per hour. So this equation is a little different. We have a different coefficient at the beginning, 4725 times our CFM times our delta W. But you can see our latent heat transfer is entirely based on how much air are we moving and what's our change in water content, and has nothing to do with the temperature of the air. The third equation is the total heat transfer. So if we know our airflow, how do we calculate the total energy to condense the water out of the air and change the temperature? So this would be both. This is expressed as a change in air enthalpy. That's our total energy of that air. So we want that Q total to be a function of airflow and our change in enthalpy, because that enthalpy factor will contain the delta for both the temperature and the water content, because that's the total enthalpy of the air. Similar steps. Density of air shows up again, delta H. So our Q total is 4.5 times CFM times our delta H. So H2 would be our ending state, H1 would be our starting state before the heating or cooling coil. Well, before and after that coil. To summarize, just to get these all on one page for you, for easy reference later. So we have our Q sensible equation. We have our latent heat transfer equation. And it's important to note, this equation is specific to W being in pounds of water per pounds of air. If you're using a psychrometric chart that is referring to things in grains, that requires a different equation. So the one I'm giving you is all about pounds for pounds. And the total heat transfer, there's actually two ways you can do that. So we have this equation that we generated based on enthalpy, or you can say our total is a summation of our sensible and our latent loads. So there's two different ways to attack that total heat transfer. Important to note that these equations, these are based on sea level air only. So those equation constants of 1.08, 4725, and 4.5, at higher altitudes, that would change the density of the air, which would change those coefficients. However, you're generally all right if you're below 2,000 feet. The margin of error below 2,000 feet is pretty minimal. You don't have to necessarily do an exact science here. But if you're going above 2,000 feet, you should definitely adjust. And there are some tables out there that will give you these equations for various altitudes. They'll just have a whole table of sensible constants for different altitudes that you can just look up, or you can derive it yourself. When we're talking about heating, we only need to worry about sensible heat transfer. Generally speaking, heating processes are pretty easy to deal with because it's simple. All we got to worry about is that sensible heat transfer. Cooling mode gets more complicated, as we usually need to worry about sensible and latent heat transfer. And that latent heat transfer part specifically can be pretty tricky to work in. That latent load typically due to a few things. One, you can have humid outside air that you're bringing into the building for ventilation purposes, because that's a code requirement. Generally, that's only an issue if you're in a humid climate, though. But if you're bringing in really humid outside air, that will increase your latent load, because that is increasing the water content of your air. You can also have moisture gain in the space due to a bunch of people. If you've ever sat in a full room that's filled to the brim with people that is not being served by an HVAC system that was designed for that many people, that's when the humidity level in the space starts to rise and you get really uncomfortable. And that's going to be true of all climates, not just humid ones. You could have some other latent loads as well, like an indoor swimming pool. At least every indoor swimming pool room I've ever been in is really humid. And so if you're pulling that air back into a cooling coil, there's going to be a lot of latent load there. And this can be pretty difficult to predict. Your dry bulb and your wet bulb outside air conditions are always changing. So a 100-degree dry bulb day with a 50-degree wet bulb temperature is very different than a 100-degree dry bulb day with a 70-degree wet bulb. The higher your wet bulb condition, the more humidity you're going to have. But both of those variables, dry bulb and wet bulb, are varying hour to hour, day to day, month to month. So that can be a little difficult to predict from an energy usage perspective, where we're trying to look at every hour of every day. Your people load, that can also be highly variable. Your space might be designed for 10 people. Well, how often are 10 people there? Maybe sometimes the room's empty, and maybe sometimes there's 5 people in that room. For this course, I like to keep it fairly easy on this topic. We're mostly going to deal with sensible cooling processes, just to keep things a bit simple. But it's important to talk about latent load, because in certain climates, that is a really, really big deal. To give you an extreme example, if you live in an extremely humid environment, sometimes you need to, let me think about this. You have to take your outside air coming in, you have to hit it with a cooling coil just to remove the air. And then after that cooling coil, you have to heat it up. So now you are cooling the air and then heating it up later, which is substantially, well, I was going to say wasteful, but it's necessary. It's what needs to be done, but it does use a ton of energy. In the Pacific Northwest, we got it real easy here. We have pretty dry air, so our latent load, at least from our outside air, pretty easy to deal with. We still have some other things we have to deal with, like moisture gain due to a bunch of people loading up in a space. But just know latent load is a big deal in some climates. That's all I got. Any questions? Cool. Any homework questions? All right. Well, I will stick around till 6:05. Otherwise, have a good evening, and I'll talk to you Thursday.
Thank you.
Thank you.